only requirement is your potential should have a periodicity, right? So x should be same as u, x plus t. So t can be say a or 2a, whatever the periodicity, right? So then you can write your wave function as this ux times running wave function ikx, right? So that's basically. So also we showed this is same as if I have x plus t, this is psi x times ei is kt, right? These two are pretty much the same thing. So let's try to use this one today for a very simple situation. So we call this a chronic penny model. If you remember, typically if you have atoms like this, right? So your potential for the electron, they are 1 over r, right? So basically, like this. That's the kind of potential, right? So chronic penny, these are two scientists, right? They developed a potential model. So you can approximate this one by something like this, right? So that's pretty close. So they developed this. So that means that you have potential, so with some periodicity, right? So that means you can use this one as example for the how to use the block wave function. So let's solve this one. The solution is very messy, but you should know how to apply that. So that's what I want to do in the next class. So this is actually, I plot this one in the opposite, like flipped potential. So the same thing, right? So just like I said, you can see this was basically, I drew this way, right? If I flip this way, that is how potential looks like, right? So now this is a good periodic potential, right? So what is the periodicity here? Can you tell me the periodicity? Look carefully. No. So actually, from here to here it is A. So this width is B. The potential width is B. That means periodicity is actually A plus B, right? So if you look at the lagging edge here, so if you start from here to here, what is the distance? This is A, this is B. Your periodicity is A plus B. That means if I write my block wave function, how should it be? X plus A plus B, right? That is so this should be psi x times ei k A plus B, right? So this is the block wave function. You have to know the periodicity because your u goes like x plus A plus B equals ux, right? That's the periodicity. Then your block wave function should have this form, right? The second form of the, remember, psi x plus t equals psi x times ei k t, right? So let's see how to solve this one. So let's do very carefully. I think if you do this one, you can approach any problem like this. So basically, you can solve your Schrodinger equation. So because that's easy, because if you take this part, what is the potential? 0, right? So then if you use your Schrodinger equation, this is a one-dimensional case, right? Psi over e squared plus ux psi x equals e psi x. So if I take this range from 0 to a, x is greater than 0, x is greater than 0, less than a. In this range, your u is 0, right? So that means you can neglect this one, then your dx over d psi over dx squared is basically minus 2m e over hy squared psi, right? So this is we call actually or something. In this region, I call this this part as k bar square, kappa square. So then that means it's your d squared psi over dx squared equals minus kappa squared psi. Then what is the solution for this one? ikx ei minus kx, right? So solution is basically psi is ae I kappa x plus be minus I kappa x. That's simple, right? Because this term is 0. So now, so that is, yeah, here, so I call that is psi in the region 1. Region 1 means this region, right? 0 and a. So this is the wave function, right? I kappa x. Kappa means given by this one, right? So kappa squared is 2m e over h bar squared. That means e is h bar squared kappa squared over 2m. That's fine, right? So now if you go to this region, in this region, what is your u is now u0, right? So that means this is basically, this becomes u0. So again, what happens is you get the same thing. If I take u0 minus e, so what happens is you get different term, right? So u minus u0. So if I do that one, so you can see in this region, you get u0 minus e instead of e here. Is that clear for everybody? So what only thing is then you get d squared in that region, d equals this u0 minus e, that's positive term, right? So times you have all these things. So what is the minus, so plus 2m u0 minus e, or e minus, yeah, divided by h bar squared psi. We call this one q squared instead of kappa squared. So then what you get is, this is straightforward, I don't even have to write, you can understand. So if you write this one, what I am getting is d squared psi over this, in this region, this you get q squared, this is a positive q squared times psi. Now what is the solution for this one? You don't get minus psi, right? Because it's a positive term. So that means your psi is basically, so it is c times e plus I q, no I qx plus be minus I q. Is that it? If you have a negative term, you get minus I, right? Sine versus shin. That's the. So here solutions are shin and cos. Here solutions are, previous one is sine and cosine, right? I think you are familiar with all these. So that means I write the solution for this part as that. This is region 1, this is region 2. So please note this here. Here you have i's, here you don't have I, right? Okay, so then here this is q squared is given by u0 minus e, because we are typical, this is a positive term because, so this is u0, we are looking at energies in this region, right? So that means u0 is larger than e, that's why it is positive. Is that clear for everybody? Now we have two wave functions for two regions. Now what we do? Is the continuity, right? So you can look at x equals 0, both wave functions should be continuous. So then psi 1 and psi 2 at x equals 0 should be same. Then take the derivative of d psi over dx at x equals to 0 also should be same, right? Boundary conditions. Typical boundary conditions are what? Your psi at whatever that x0 value, first one should be same the second region. Also derivative of this one at this one should be same as at x. That's fine, right? So now if you do that one, what do you get? First one is very easy. X equals 0. If I put x equals 0, this becomes a plus b equals here c plus d. Okay? This first equation is straightforward. So if I use so these are the two equations, right? So then x equals 0. Is that clear for everybody? Yeah. Now if you take the derivative, what do you get? If I take the derivative here, you get ik out, right? So here also you get minus ik out. Now we put the x equals 0 for both, then you get this one. Is that clear for you? Derivative that x equals 0. Now we have to do for x equals a, right? So this we did at x equals 0. So now because we have so our wave function was something like this, right? So this is 0, this is minus b, this is a, right? So this is psi 1, this is psi 2. So now if I want to calculate psi 2 at now we did at x equals 0, right? Now if I want to do at x equals a, how do you do that? We know psi 1 from how to get x a, right? Because psi 1 we know how to put x equals a. But psi 2, it is not valid in this region. Then what can we do? You can use the block theorem. Psi 2 at this point is same as psi 2 at this minus b times ei k. So you can use this equation. In this one, so far we didn't use any block theorem. So if you want to do this one, so you have to, if I want x psi 2, right? Psi 2, if I want psi 2 at x equals a, right? That's what we want, right? If I want at x equals a, what do I get here? Psi x equals a means your x has to be, here x becomes a, so x becomes minus b. If I take, say x equals minus b equals what? If I put x equals minus b, then this b and this b cancel, then you get psi at a. That means psi 2 at a, that's what we don't know, right? That you can write as psi 2 at minus b times eik. So this is the block theorem. So that's what we do here. So x equals 0 is fine, right? Now how do you do at x equals a? So we know that for the this one you can do the x equals a, that you get eik. Yeah, that's fine, right? So that part is there, but we don't know the psi 2 at a because that's not valid there. But you can use the block theorem to do that. We know that one should be equal to psi 2a, but psi 2a you can get from this equation. Psi 2a is basically this psi 2 minus b times eik. Think about that. So if you do that, what you get here is, that's the psi 2a, right? That's what I got. This is basically the Bloch's theorem. So now you have psi 2a, so now you can equate these two, and also you can get the derivative of that one. So I don't know how Everybody comfortable with that? So that's how we use the block theorem. So until here we didn't use any block theorem, right? We just simply solve the Schrodinger equation for two regions. But now we have to use the block theorem to get here. So now if I use at x equals a, you just put x equals a here, or this thing, right? This equals, now I can write as, you know, psi 2b minus b. That is CE, x, you put minus b, right? So then you get that equation here. Is that clear, everybody? Psi 2a, you get, sorry, here. Yeah, this one equals psi 2a is, just put minus b here. Everybody fine with that? Think about that. So now you can do the same thing if you do the derivative, right? So if you take the derivative of that one, you can see if you take the derivative of this one, you get q. So from first one, right? You get ik out. Just put that x equals a. Then you get again if you take the derivative of this one, you get q here. This coming from the wave function continuity, this coming from the continuity of the derivative. Okay, that's it. So you have 4 equations now. So you know how to solve the 4 equations. So if you do this one, you have like this A, B, C, D. This coefficient, right? You can write actually this like a 4x4 matrix, so determinant here. So if you write these 4 equations, you can write all these things together. Like first equation is a plus b plus c plus d, right? So this 0, that means all the, actually 1 was minus something. Yeah. If you put a is 1, 1, minus 1, minus 1, right? You know how to write the determinant. 4 equations, so then this equals 0, then what should you get? Your determinant should be 0. No? If you have 4 equations with these 4 coefficients, you know how to solve it, right? So now you can see it's not very easy. Everybody knows how to do the determinant, right? So all these 4, we have 4 elements, 4 by 4. You know how to take this one and multiply by this matrix minus this one. Everybody familiar with that matrix manipulation? If you do this one, actually you get this is the equation you are getting. It's a pretty not very easy expression, but not too difficult. So we have very symmetric terms, right? That's why you are getting the shin term, cosh term. Everything coming from these things becomes shin and cosh, right? Everything coming from I term will have sine and cosine. It's not too difficult. So that is the final equation. If you want, you can easily do this one.
That'll be a nice homework problem.
What's that?
That'll be a nice homework problem.
Homework problem. I don't know. You haven't done this problem in quantum mechanics?
I think so, yeah.
Oh, because the block theorem is not used in quantum mechanics. That's why. Is clear for everybody? Did you see where we use the block theorem to get that at x equals a, how to get the continuity, right? So for that you have to use the block theorem. Okay, so this is the precise expression for this one. Now you have to be very careful. What is this kappa, q? These are just that expression, right? Kappa is coming from E equals x squared, kappa squared over 2m. Then q coming from u0 minus E equals q squared over 2m, right? That's how you got this one. but this k coming from the block wave function, because we wrote psi x plus this a plus b as psi x times eik a plus b, right? This k is the block wave vector. So this determines your wave. So that's a state given by that each wave function. So this simple case what we are interested in. These are just the constants, right? Q and kappa. So this k is called the block wave vector. Because that determines, because that's the, you have k dot r, right? So that determines your block state. So this, each electron is given by this 1k state here. Okay, so remember now, so here we talked about your, so they have width b and height u0, and periodicity basically if you start from here a, right, periodicity is actually a plus b. So this is not easy to evaluate, right? So we make an approximation here. We make this potential width very small. So we make b goes to 0. That means you are making a delta functions, right? It's like a delta function potentials. If you do that one, you can see you can make some approximations. B is 0, then right side becomes cosine. This is Ka, right? That's fine. Because B0, we are making B0 equals here cosine kappa A. So here cos QB. So when B goes to 0, cos becomes what? 1, right? So this becomes 1 because that's basically EIX, sorry, no I, right? EX plus E minus X divided by 2, right? When it's equal 0, 1 plus divided by 2, this becomes 1. So you get simply this 1 plus, this is little tricky. So this shin QB, we know one thing, when B goes to 0 or X goes to 0, shin X over X goes to 1. Right? So we'll make some manipulation here. I will write this shin Q. If I do this one, what I have here is I have shin QB. I write QB here. So then this Q is there. There's no B, right? So I have to put B in the upstairs, right? So then this is. So this Q is already there. So then I have 2 here. Then Q, yeah, I took Q out there. Right? Then upstairs I have Q squared minus kappa squared. These are constants, right? This is same as that one, right? Q squared minus K kappa squared, 2, then Q, I need, yeah, Q is there. Kappa is not there, so that means I need to have kappa here, right? Yeah. Is that clear? B. Yeah, that's it, right? Now everything is there, right? So now this term goes to 1. So then what you have is basically I have then I have in here I have Q squared minus kappa squared times B over 2 kappa, right? That's it. That's the equation. So now we know Q is bigger than kappa, right? Because kappa is simply that E, but Q is U0 minus E. That means Q is much bigger, not bigger, but if you take the square of that one, that becomes much bigger. So then you can ignore this one. So then we can write this one as Q squared B divided by 2 kappa plus cosine kappa A equals cosine Ka. This is important. That is the yeah. That's it. So if you do this one, so typically they call this one as P. If you write, they introduce some factor P as Q squared B A over 2. So that means I can write Q squared B as Q squared B over 2 as P over A, right? So this is P over A. Then we have kappa, yeah, you get the answer. P over kappa A plus cosine, you know how to do this one, equals cosine K. That's the equation for this delta function like potentials. Okay, so now whole idea is to solve for K. So how do you do this one? That's also not easy to solve this one. So what people did was, you just plot this side of the function and draw this side of the function and see where the two curves intersect. That's a solution, right? So that's how they did that one. You can see if I draw this part, it looks like this curve. So then I write cosine Ka. Cosine Ka can be only between plus and minus 1, right? So this is the curve for this term. So then I draw plus 1 and minus 1 curve, because cosine Ka can be only between these two. If you do that one, you will see regions above plus 1 and below minus 1. So they are not allowed, right? Because cosine K can be, we know sine and cosine. Cosine can be only between 1 and minus 1, right? Sine also same. So that means these values are not allowed. The ones marked in blue are not allowed. So then we know this where these are going to be intersected. So cosine K, we know it's a plus 1 minus 1 becomes pi, 2 pi, like that, right? Cosine 0 is 1, then cosine pi is minus 1, and so on, right? Cosine 2 pi is plus 1, so you can see, you get pi, you get minus 1, this is where it is cut in at 2 pi, you get plus 1, then it's cut in here. You get the idea, right? So that means you have, can you think now what these regions will correspond to? These are not allowed, right? So this is exactly where the band gap is holding, right? So if you draw your energy, because energy we know given by either h bar squared is kappa squared over 2m, or h bar squared q squared minus e over 2m, right? So this u0 minus e equals squared q squared over 2m. From here you can calculate your e. If you do that one, so actually it's really nice. So you will see until pi you have this parabolic function coming from this k, right? So then at pi what happens? You have that region where the value becomes more than 1, right? So that's exactly where the band gap is opening now. See how beautiful that one. Then again when you come to 2 pi, again you have region. This is the region in that curve. I showed the region that's above this one, and this is the region that's below. These are exactly the band gap. See how nicely they could explain the band gap formation. So remember this is Ka, that is the block wave vector. now you can fold it back to that means we know this is first brilliant zone, second brilliant zone, third brilliant zone. You can fold it back, then you can make this kind of band structure, right? If I fold this one back, it becomes this one, right? Sorry, this one. No, that is it's still in the first brilliant zone. This one, you can fold it back to this side, right? So this, actually the chronic penny model can really produce this band structure with the exact band gaps happening. That's pretty actually neat, the idea. Yeah, quantum mechanics, I'm sure the reason you don't do is you don't know the block wave, block theorem, right? That's why. Otherwise, it's a very standard problem. Okay, so we can actually calculate this one. So you can write a simple program to produce this one. So here is something I calculated for. So because my periodicity is A plus B, right? Please remember. So that means if I put some numbers, I just recreated this extended zone band structure. You can easily do these things. Okay, so I'm not going to talk too much about that. So now you understand how you can use the block theorem to solve simple this periodic potential problem. Everybody got where we use the block theorem? So this is the place we use the x plus t equal x here. And only the period was a plus b, that's the only difference. Okay, so now let's actually talk about the density of states in a periodic potential. So if you don't have a periodic potential, your density of state was simply the square root of E function, right? But if you have a periodic potential, we have a band gap, right? That's what we showed. So then what happened? Density of state goes to 0, right? So that you have to, it has to happen with some continuity. So this is some density of states for different like monoatomic, diatomic and triatomic ones. You can see S orbitals, they have this exact square root of E, right? So then it has to come to 0 whenever you have this band gap. So it cannot just come like this, you have some this kind of filter. So then at this point, it's like a band gap here, right? There's no. So then if you take p orbital electrons, p orbitals have much little higher energies, right? So then they show this kind of behavior. Then again, if you have band gap, they should come down here. Can you tell me if you have a d orbital, how does it look like? That will have much larger, that's very important thing to remember. D orbitals have much higher density of states. Typically, if I draw density of state E, d orbitals will show like this. Because others show simply standard, right? But d orbitals will show much higher. So that's why they are very good for the catalysis and things like that. Any transition metal with d orbital electrons, so they have much higher. So this is something to remember. So typically, somebody asks, you will tell your density of state is simply for 3D measure, right? So it looks like this. But that's not true, right? Whenever you have a band gap, it should come down to 0. That's how it looks like. So here, even both p orbitals also, we have a band gap. Everything should come back to. Here we are showing Fermi energy sitting somewhere here. Everything below Fermi energy, they are all filled, right? So above everything is empty. Oh, unfilled, right? Okay, so now let's talk about something, another consequence of block theorem. I think everybody remember we introduced, for the phonons, we introduced phonon wave vectors, then phonon energies, and phonon dispersion relationship, everything, right? Now we are going to introduce same thing for block electrons. So we know, just like phonons, we introduce the group velocity for the block electrons as same as before. So typically everybody remember this? This was a long time ago, right? D omega over dk, one-dimensional case, or if it is three-dimensional case, you can write this one as write k omega, right? Yes. So two-dimensional case, one-dimensional case, basically we can write like this. So then, yeah, that is the case for three-dimensional case, right? So this omega has some dependence, but the reason we introduce omega for the phonons, because we introduce our energy as h cross omega, right? That's the simple harmonic oscillator energy. But in this case, we are mostly talking about E, right? Energy given by either this one or like graphene, remember, is simply something proportional to k, right? So whatever the k dependence. So that means we have to introduce Vg in terms of energy. How do you do that? So basically we always this energy is h cross omega, right? So that means I can, because these are waves, these block waves, right? Block waves, you can write energy as h cross times omega. That means Vg you can write as omega, you can write as 1 over h cross E. That means I can write h cross dE over dT. That's the group velocity for block electrons. Or you can write in three-dimensional, this is basically grad k E. So that is the group velocity for block electrons. K is the block. So this is what that one. Please remember this one, dE over dK or grad k. So but you have to be very careful. So now let's talk about so dynamics of electrons in an electric field in this K space. So if you consider in a real space, remember your current density, anybody remember? Given by time speed, right? So if we have, this is for one electron, if we have a group of electrons, your total current density becomes E n, actually your all V's, right? You have to add all the V values. So that means you can, each one has some K vector, right? So it depends on your K. So J, right, like this. So then if you look at V in terms of E, so we have to be a little careful like this. So if you take the symmetric wave function, so this is a plus K, so this is minus K, right? If you take, so energy is same, right? energy for plus K minus K, that means energy plus for plus K is same as energy for minus K, right? Because they are symmetric, right? Any point if you take positive K, you get this value E. If you take same negative value, you get the same E, right? So now that's important because what is V? V is dE by 1 over H cross dE by dK, right? So now for the plus K state, if you take the velocity, if you take dE over dK, you get plus K coming out. If you take for the negative K value, you get negative K coming out, right? Negative sign. That means your group velocity is opposite for plus K states and minus K states. Is that clear? Because you have to take the derivative. This is important thing to remember. So let me write this one. So V is like this, but because of symmetry, this is clear, right? So then if you take the derivative, your V minus K should be negative. Why is that? When you take the derivative, E plus K, you get plus 1 out, minus K, you get minus 1 out, right? That means velocities are opposite. So if you take some electrons with positive K state, velocities from the other side are negative. So that means if you have the symmetric band all filled state, what's the total velocity? Going to be 0. So that's why filled bands, we talk about that. If you have filled bands, your total net current is 0. It cannot contribute to any currents because all the J, because J has this one, right? If you add all these things, this term becomes 0. It's a symmetric band, right? So that is very important concept to know. So if you look at this one, so total V becomes 0. This means field energy bands carry no current. That's what we talked about, right? Because it cannot carry any currents. So this is very important thing. But that doesn't mean they are not moving. That's some people misunderstand that. So this doesn't mean electrons are not moving. They move in opposite directions, right? So that's why they cancel off. Please remember this one. Electrons in field bands are not stationary. They are just the same number moving opposite directions and cancelling each other. But that is not true if you have unfilled bands. So before that we talk about this something very important theorem called acceleration theorem. So we can show this one. Everybody remember, if you have what is power? Power given by your time derivative of your work done or energy, right? So then also we know work done means what? F dot dr, right? So that means if you take F, dr over dt is basically velocity. So that means I can write my power as force times velocity, right? So force times velocity. Then also if I take work done is basically energy. So that means I can write this one as dE over dt, same thing, right? So now we know E is given by 1 over h cross, sorry, Vg is given by 1 over h cross dE by dk. So that means I can write this one as dE over dk times dk over dt. Is that clear? So dE over dk I can write as h cross times Vg, right? Times dk over dt. So this is equal to F times this Vg, right? F times Vg. So now you can see Vg cancel, you get F equals H cross dk over dt. Very important here. Force is given by H cross times how the k vector changes with time. So this is called the acceleration theorem. You can follow the derivative. F is given by H cross dk over dt. This is acceleration theorem. Derivation is simple, right? You can follow through. So you can now use this equation to calculate how k changes with time. That's what we want, right? It's easy to do in the, not easy actually, it's difficult to do in the real space. In real space you need to know how position changes with time, right? But this is very difficult to do. But you can easily calculate how the wave vector changes with respect to t. So that's what this acceleration theorem is about. So now you can think about this force. Also you can think about force means what? Rate of change of your momentum, right? So but this momentum is not really the momentum of your electron, because if you talk about momentum you have to consider total force. But here we are only talking about the external force. Really you have a force coming from the lattice also, right? So for that reason we don't call this PC as electron momentum. We call this same as phonon is a crystal momentum. Because if it is a real momentum, you need to have the total force. Because there are two things happening, right? You apply from outside, then you have force coming from the lattice of the electron. So PC is basically H cross omega, right? If you write these two together, F is H cross dk over dt, then also this is H cross times PC, right? Sorry, dp over dc. If you consider this one, you get PC equals simply H cross times k. So this is called the crystal momentum. You can compare these two, right? That's okay. dpc over dt, that means H cross k equals pc. This is it. Okay, so now let's try to solve this acceleration theorem. So now let's see if I said this external force, right? Let's see, this force is just the electric field. So now if I apply electric field, so what is this one? Is the acceleration theorem, right? Then I can write my external force as minus E times E. Now you know how to solve this one, okay? K is basically EE over D. You can simply I can write dk over dt is, so it's one dimensional case, minus EE. EE, that means k is, you have to integrate over t, right? Suppose in the relaxation time approximation, so this becomes EE tau, right? Or the have H cross here. So this becomes EE tau divided by H cross. So, but ideally you can do this way, dk equals minus EE over H cross dt, then you have to integrate, right? But here E is a constant. Suppose if I give some E has some time dependence, so then you have to do the integral, right? But in this case, E is basically constant, right? So that means you can easily calculate your dk as, so this is, okay. Is it clear for everybody? So now if you look at this one, what does this say? If I have electric field, your dk is going to, with time, dk is going to decrease, but you have negative E here, that means k is going to in the opposite direction of E. So that means if you have electrons like these, right, initially suppose this unfilled band. Filled band we know that nothing it can do, right, because total current will be 0. But if it is, say, half filled or partially filled band, what happens here? So this is your K. So this one has certain K value, right? So now when you apply electric field, what happens? That K value will change by dk. So suppose if I apply electric field this way, so then dk is going to be positive direction. That means you will see this one, after some time it will move by dk. So all these electrons will start moving that direction. Right? So that's a constant electric field. If it has a time dependence, you can do that one. So when I apply electric field, what happens is these electrons will, in the k space, they are going to move like that. Because dk is going to change. That means your k position is going to. So initially it was here, now it is here. So because of the electric field, now you can. So then what happens? Once it comes here, what do you expect? Actually that will reappear from here. So it is coming like this, comes here, then. So actually people have observed this one very clean material that is called the block oscillations. So with time you will see this moving means you have current, right? So this current actually, so here you have what is the velocity in this case? These electrons have velocity because velocity is given by dE by dk, right? So here your dE or dk is positive. Here dE or dk is negative, right? So that means these electrons have positive voltages. So that means it is going here. They reappear here with what velocity? Negative velocity. That means your current is oscillating. So people have observed this one, your current doing oscillation because of this block oscillation. But that time is very small. So like 10 to the power 15, minus 15. That means that's a time, right? So that's a real small time. So that's why hard to observe that one unless you have a really clean material. So I think whole thing is about solving this. Okay, and how that changes. I will give a homework problem to work on that one. So we can see symmetry is j equals 0. Here they are going to k value increases. So yeah, here you can see I just draw velocity. Here what is the slope? 0, right? Velocity 0. Now slope is increasing, then decrease and becomes 0 here. Here slope is 0, right? This is how the velocity looks like. That is the dispersion relationship. Yeah, so minus k. AC current is predicted to result from DC field. By applying a DC field, you can expect a AC current, right? So this is somewhat similar to just something called the Anderson oscillations in superconductors. That's somewhat similar to that one. Okay, so these are, like I said, this time is almost like 10 to the power minus 14. So that's why it's very hard to observe that. Okay, so now we can write that this one, like we said, if you solve this one, if you take time like relaxation time, tau, then you know how to calculate dk and everything. Is that clear? Delta k is given by this one. So, yeah. So that means, what does this mean? If I apply electric field, then your delta k is moving in the opposite direction. So that means if I draw my, we talked about this one, right? So this is my Fermi surface with Kf. Now if I apply electric field, delta K is in the opposite direction, move it by how much? By this much at time tau. That means actually this one is kind of shifting. So this distance, this delta K is given by, this delta K here is given by that value, EO tau. Tau divided by exactly what happens. The same picture, right? In electrons move in opposite direction and Fermi surface delta K move in that way. Yeah, this is what we talk about delta K. So now we can think about this one. Let's quickly calculate the electrical conductivity coming from this movement of the Fermi surface. So in this one, what is the total current? 0, right? Everything is filled. So you have plus Vk, minus Vk, everything is cancelled. Now if I move this one, so you have this extra delta K coming from here. Because of that you have current. So that means your total current is given by J is EnV. You need to know number of electrons in this one region, right? So only from that one, then we need to know the velocity in that. We call this uncompensated electrons because these are compensated, right? Everything plus minus. So we need to know number of electrons in the uncompensated region and the velocity, total velocity of sum of the velocities in that uncompensated region. So that's why we have to. So if it is completely filled, this is 0. It's clear, right? V plus minus, so because they are in the opposite K values. So now that means your total J you can calculate total number of electrons in the uncompensated area, the region, times your E times velocity of that region. So how do we calculate that? That's pretty simple. How do we calculate this one? So that's dN, right? dN is basically N density of state times delta E. So delta E you can write in terms of delta K because E is given as remember how E and K are related. So if you know E, you can calculate delta E. You can relate to delta K. So here, but in density of state, only you have to consider near the Fermi energy, right? Because this is the Fermi energy, Kf. You don't have to consider anything much larger or anything smaller. You have to calculate density of states only at the Fermi energy. So that's it, very simple to calculate this one. So if you do this one, what you get here is given by, this is what your density of state times delta E, right? That's the total number of electrons in that region. dN equals N, but we have to only consider density of state near Fermi energy. NEF times delta E times charge times average velocity. So now we can go ahead and substitute this one. So yeah, so if you do this one, I can write this delta E. So this is NEF times E times VFX, VF, that's the X component I'm trying. So it's only the one dimensional case. So then VF you can write as, if you remember, Vg is given as 1 over h cross dE over dk, right? So if you plug in that, you get, so delta E, sorry about that. So delta E you can write as delta E over delta K times delta K, right? So what is delta E over delta K? That is Vg, right? Vg equals 1 over h cross dE over dk. That means dE over dk I can write as h cross times Vg, right? Cross times, that's what we have here. H cross, yeah, it's pretty straightforward. Yeah, h cross times V, I just put delta E as that this VF is still here. Here I got this one times delta K. Is that it? Delta, this delta K. Is it clear for everybody? So now I can go ahead. What important thing is you get square of this VF x square times NEF, then you get now delta Kx. We know the acceleration theorem, h cross dk over dt is your EE, right? Force. So that means your dk is basically EE tau over h cross. dk you can write as EE over h cross times tau. That's it. So now Jx is this one. So but now we have to be careful. Now here we only considered x component, but we have x component squared. If you take the three-dimensional v, we know v squared is given as vx squared plus vy squared plus vc squared. That means this one I can write as 1/3 of v squared, right? So that's where the 1/3 term comes. If you do that, you get this is still same. Then I replace this one by this 1/3 term. You get Jx equal this one. See? Straightforward. J equals sum times Ex. So what does that mean? Your J equals sigma. If you know J and sigma, this should be sigma. So that means you can write sigma as this one. If you do that, you get sigma as this one. So now, if you remember, you did the homework problem, NEF has 3n divided by 2 EF, right? So if you plug in that one, you can easily, I encourage you to do yourself. If you do that one, you get sigma as n squared tau over m. That's the Brugger conductivity. Please plug in all these things. 1/3 E squared, Vf squared, tau f. Here we write as 3n over 2 EF. EF I can write as half m Vf squared, right? So then Vf squared cancel. This 3 cancel. This 2 cancel. You get exactly that one, right? E squared tau divided by n times e squared. Yeah, times n. Yeah, so that's it. Just you have to use that relationship we did in the homework. You can see nicely how these 3 and these 3 cancel, these 2 cancel, then Vf squared nicely. Ef you can also write as half m Vf squared, right? If you do this one, you get exactly m squared tau over. Is that it? So this is how you. Now you can see we did this formalism in real space as well as momentum space. That's what I wanted to show you how we do these things. Okay, so next let's quickly do. So there's something called, very important thing, the band mass. That comes from this the block formalism. So typically we talk about mass here. So that's a free electron mass, right? So when we talk about this, sigma is sigma is n squared tau O m. This is we call the free electron mass. But what people try to do is introduce same formula even with other effects are there for the particle. So, but that mass then will have a different meaning. So we usually call that one as some effective mass. So but the formula would be exactly same. So effective mass means it's already all the effects on that particle is already embedded in this mass here. That's called the effective mass. Before that we'll talk about the band mass. So let's start from it. Much time. Let me go through this one. Acceleration you can write as the time derivative of velocity, right? That you can write as dv over dk times dk over dt. Is that clear? Now we know how to dk over dt, how to connect to force, right? So that's basically, yeah, ax you can write as dv over dk times, yeah, let me, it's very straightforward, I don't even have to write. So, is this clear? dv over this equation. Now I want to do this one and this one separately. This one, everybody remember, what is this one? That's basically acceleration theorem, right? F is basically, F is h cross dk over dt. That we know. This part is easy. To get this part, we can write dv over dk as d over dk times vg I can write as, that's the definition of this one. If you do this one, what you get 1 over h cross d squared e over dk squared. So now, if I put it here, what do I get? Ax, I can write ax as dv over dk x we write as 1 over h cross d squared e over dk squared. That is dv over, only this part, right? dv over dx. So times dk over dt. Exactly. Then acceleration theorem says force equals h cross times dk over dt. Right? So that means I can write this dk over dt as dk squared. dk over dt is basically f over h cross, right? F over h cross. So you can write this one as ax equals 1 over h bar squared d squared e over dk squared times f. What is this? Newton's second law. F equals ma or a equals f divided by m. That means, this means mass. We call that a band mass. So band mass is given. This is different from the free electron mass. So mass is given by 1 over, right? That means h bar squared divided by d squared e over dk squared. This is very important relationship. This is called the band mass. So let's take a simple this kind of band structure. Then what is E? K squared over 2m, right? Parabola. Then what is dE over dk? Is h cross squared k over m, right? So then what is second derivative? H cross over m. So now if I plug in here, what do you get? Equal h squared divided by this square. This is h squared divided by m. Then m goes here. So then this one, this one. This is same as the free electron mass. If you have a exact the free electron band structure, your band mass and the free electron mass is same. But you can imagine if this is different, right? For example, if you take graphene, what do you expect the band mass? Graphene has this kind of band structure. Your second derivatives actually become infinite because this doesn't have curvature, right? So that means this one becomes 0. Okay. This divide by this is infinite means if you divide by this one, your effective mass becomes 0. That's why graphene, your effective mass is actually 0. So that's why you cannot use Schrodinger equation. Schrodinger equation has this term. It has a mass. That's why for graphene you have to use Dirac formalism. So it's for massless particle. Okay, so is this clear? Now we can define our minutes. So if you do this one, this is your band mass or effective mass is given by, usually we call this one n star. Bar squared over. So sometimes it's easy to write this way, right? So people usually write 1 over n star as 1 over h bar squared e squared e over e squared, rather than putting this one in the denominator. Same thing, right? So we showed, yeah. Where's the, but this is not real simple. If you take a real 3D material, this mass is actually the tensor. So it has 6 or 9 components, right? So you have this 3 by 3 tensor. But we are not going to talk about that. So we basically talk about only single scalar masses. Okay, so that means if you have, yeah, this is the last thing I want to talk about. So if you take, say, you have one band like this and another band like this. So everybody remember the curvature? Actually, second derivative means really the curvature, right? So this one has much larger curvature, right? So because if it is flat, 0 curvature, right? So this becomes smaller curvature. This means larger curvature, right? Curvature means second derivative, right? So this one has smaller curvature means that is in the denominator. That means your effective mass is higher. If you have a larger curvature like this, that means this is large means effective mass is smaller. Please remember that one. So you can see here, this one has larger mass because your curvature is small. Here, this is curvature is large, that means your mass is small. Okay, I will stop here. So then you can see how you calculate these things. If I have band structure like this, your dE or dk, you understand this one, right? Because this increases, then starting to go down. If you take the second derivative, you can see it's a constant here, then this becomes indefinite, right? So then it becomes, here it becomes negative. You can see in the band, the band mass changes depending on where you are. If it is here, you have one effective mass. If you are here, you have different mass. Also, if it is like this, then your mass sign also changes, right? That's why we are going to introduce the electrons and holes. So that's the last thing I want to do. I think next class I am going to finish this chapter. Then we'll start with the semiconductors. Okay. answer. You didn't send me that Raman plot, right? You did?
Yeah.
Oh. Yesterday?
Yeah.
Oh.